Hello, this is the next video in a playlist that I'm calling Parameter Estimation. And here we're going to derive unbiased estimates for the population standard deviation using the sample mean absolute deviation and the sample standard deviation. So let's let xi be IID normal with mean mu and variance sigma squared. And our sample size is n. We're going to denote the sample mean deviation by sigma tilde, and it's derived like this. It's the sum of these deviations from the sample mean. Now let's look at this in a little more detail and do it in steps. Let's let yi equal this difference in here. And if we derive the mean of yi, that's expected value of each individual, and both of those are mu, so it's 0. So the expected value of yi is 0. Now the variance is the sum of these variances minus 2 times the covariance. Well, the variance of xi is sigma squared. Variance of x bar is sigma squared over n. Then we have minus 2. And this 1 over n in the x bar, let's take out front, and that's what this is. And then we have xi, or the covariance of xi and the sum of these x's. But xi is independent of each one of those except for xi, and so the covariance would be 0 except for that one term. So the covariance of xi and xi is actually the variance of xi, which is sigma squared. Now we can factor out a sigma squared and simplify, and we get this. So now we know that yi is distributed with mean 0 and variance this, sigma squared 1 minus 1 over n. Now I'm going to reference a video, the mean and the variance of a folded normal distribution, and I actually just put a video out after I already written this video up, mean and the variance of a half normal. Both are applicable, and you'll see why in a second. The absolute value of yi, where yi is normally distributed, is what's called a folded normal distribution, and it has the parameters what mu and variance, whatever the original were. But here the mean is 0. So it ends up being what's called a half normal distribution, and it only has one parameter, the variance of the original data. And the reason we have to look at this is because when we take the expected value of the mean of yi, then that's a half normal distribution. And the mean of that is this. It's the square root of the variance, which is this, and so that square root comes out, but this piece has to stay in, times the square root of 2 over pi. And then this can be simplified to this. And this expression is 100% derived in both of these videos. Now, since this is a constant times sigma, we can take the reciprocal of this times the sample mean deviation, which is what we do here, to create an unbiased estimate. So the mean of this, now this is a constant, so it comes out front, and then the expected value goes into the sample mean deviation, into this. Well, we just derived the mean of this, which is this piece here. Now this constant cancels with this, and we're summing sigma n times, so we get n sigma, and the n's cancel, leaving just sigma. So this is an unbiased estimate for the population standard deviation using the sample mean deviation. So here we're going to let sigma hat be the sample standard deviation, and we're going to use the sample variance that's unbiased, meaning we divide by n minus 1. And now we don't have to, because it's just a constant that we would have adjusted in the end anyway. But let's break this down. If we let yi be this sum here, so the sum of the xi minus x bar squared over the population variance, this can be easily shown to chi-squared distribution with n minus 1 degrees of freedom. I have several videos illustrating that. Now if we take the square root of y, call it w, that's a chi distribution with n minus 1 degrees of freedom. Now I have a video called mean and variance of a chi distribution, which may be applicable in this video. Well, it is applicable, because when we take the mean of W, which is a chi-distribution, it turns out to be this: square root of 2 gamma of n over 2 gamma of n minus 1 over 2. Now, what we're going to do is take this constant time and take the reciprocal times what we did over here, and I'll show you in a second. Now, remember that, oh yeah, we took W. So we take this reciprocal and put it here, and then we have the sample standard deviation here. Now, the next step is quite interesting. This here is a constant, so we can take it out front, and that's what this is. Now, the divisor in this, that's n minus 1, so it's the square root of n minus 1, that's what this piece is. Then you're wondering, well, wait, what about that sigma squared? We multiply by 1. We multiply by sigma and divide by sigma. So when we take that sigma under this square root sign, it actually becomes sigma squared. And you can kind of think about it, if you take it back out, it would be 1 over the square root of sigma squared, which is sigma, and that would cancel with that. So we literally just multiplied by 1. Now, this is the expected value of that chi-distribution, which we said was this. Well, we take, yeah, and then we get cancelizations everywhere, right? This, and then that constant, and n minus 1 and this, everything cancels, leaving sigma. And I'll let you do the math there. I ran out of paper on the bottom. Now, one more property, and then we'll call it quits for this video. We're going to show that the mean absolute deviation is always less than or equal to the population standard deviation. And we're going to do this using Jensen's inequality with the convex function f of x squared. Okay? And Jensen's inequality is f of the expected value of x is always less than or equal to the expected value of the function of x. And I have quotes around this because I have a video called Jensen's Inequality with Applications, where we prove Jensen's inequality 2 different ways, and then we use it in some interesting applications, statistical applications specifically. So here, f of the mean, and so we're going to let x be the absolute value of x minus mu. That's, in quotes, the new x. So, and then f is the square root, and that's where we get the squared there, right? An expected value of this. That's less than or equal to the expected value of the function squared. And remember, x is the absolute value of x minus 1. We take it, put it in this function, it squares it. But absolute value squared is the same thing as just squaring it. Well, the mean of this squared is we know is the variance. Well, if you take the square root of both sides, you get the expected value of absolute difference minus the square root of the variance, which is the population standard deviation. Well, these results we're going to point back to in later videos in this playlist called Parameter Estimation. Well, I hope you enjoyed this. I sure did. Please like the video and subscribe so you don't miss the next one. Thanks. Bye.